Is going to take, I'm waiting for the beeps because sometimes it still does the countdown. No countdown this time. Oh, it keeps getting farther behind. All right, 8.4. So this is going to take us and go one more layer deep. This is stuff mostly that we've done before. It's just kind of adding a little bit from over here and a little bit from over here and putting them all together. So hopefully this will make some sense. I think I'm going to go through a good amount of this quickly and then maybe have a couple more videos where I'm working through some problems. Okay, the biggest thing with this, if you recall, acids and bases, when they're mixed together, especially a strong acid and a strong base, you learned in Chem 1, has the same net ionic equation. It's going to be H plus OH negative equals H2O. And then, of course, there's a salt that's formed with it as well. So with this, that's the simple explanation, but there's more complicated things with it. What if we have a lot of a weak acid and a little of a strong base? Or what if we have a lot of a strong base and some of a weak acid or a strong acid? I think I may have said the same thing twice. Okay, a lot of this is going to start off with dilution. M1V1, M2V2. You can move, or you can voom, whichever you want. We're going to have the stoichiometry then. You'll be able to see what's left. So the idea behind this is if we say that we start off with a 0.1 molar solution of a certain acid and in this amount of liquid, and then we combine that with 32 milliliters of a 0.2 molar solution, even if you're not adding any more acid to it, your hydrogen ions are not as concentrated now as what they were before. That's just something to keep in mind. Stoichiometry and then ice tables will come into play with that. Okay, so this is explaining the same thing that I just explained in the notes, but it's kind of big and colorful. If you want to look at that, you can read through this more. Pause the video if you want. Okay, I've got a few different tips where I added probably a lot more information than what you needed. I think it's probably going to be the most helpful just to start looking at some of these. This is what I just said, but you have the basic reaction, which is our hydrogen to our acid, then becomes our acid without the hydrogen ion, forms water, forms with the hydroxide. So something like HCl. This would be the chloride here, and this is going to combine with, let's say, sodium hydroxide. So remember that those are going to bring the hydrogen ions or the hydroxide ions to form water. We have our dilution, and then we can use our stoichiometry after we figure out what things are and then do our ice table. Okay. To explain pH, when we have no base added, maybe this is just a dilution, or some base added, but not equal. So again, no base added, we just have the negative log of our hydronium. If we add some base, then we have to figure out what's been offset and then what free hydrogen ions we have left swimming around. That's kind of one of the big things that we're calculating. And so once we figure that out with some stoichiometry, we'll take the negative log of the moles of acid that are left over. If you get to an equivalent point, then you're at pH 7. And if you have enough base, so let's say we have a weak acid, you've got acetic acid, vinegar, and you add something like some strong base of sodium hydroxide, now you're going to have enough base to go past the equivalence point, and then we're going to use our pH 14 minus our log to get the base that's left over. Okay. Move me out of the way here. So if you have one weak and one strong, this gives you a little bit more information with this. There's no base added. Basically, you'll just use our ice table to determine Ka, which is what we've been doing with some of our weak acids. If you have some base added but not equal, you'll take the pKa plus the log of the salt over the acid, and a few different ways. Rules both ways. Again, one of the things that you probably have found from this chapter, this unit, is that there's a lot of different ways to kind of get to those different spots depending on what you're given. Make sure you understand the relationships of those. Okay, here is an example from Dr. Dina. Okay, she does a great job with this stuff. Determine the pH when the following solutions are combined. So this is what I was talking about just a minute ago. So we have a volume of perchloric acid and a volume of potassium hydroxide. Hopefully you remember perchloric acid is a strong acid and potassium hydroxide is a strong base. So we can assume that they will go towards completion. This gives you our volume 1, molarity 1. We need to figure out molarity 2. There's no slot for volume 2, but you should know that by now, that's because you add these two up together. Okay, so we have our 35 milliliters times our 0.2 molarity equals 35 plus 25 for our M2. And then you can do the same for our base. So even though we're mixing these together, we're focused on the hydrogen content and the hydroxide. We get different molarities. Okay, so now our molarity is no longer 2 because it's the same number of moles of acid out of a larger volume. It's the 35 plus 25. So that's 60 milliliters instead of the original 35. That's how your molarity goes down. You might be saying, Mr. Davis, of course we get this, but I hope that some of you are like, oh, okay, that makes sense. Now the stoichiometry. We see what this would be if we were to add these together to make sure that we don't need 2 of one of these to go offset one of these. But it's a 1-to-1 ratio, so that's pretty simple. And now we have a before, shift, after. Again, it's pretty much the same thing. It's just somebody in class today said very well, like there's too many KAs, there's too many A's, there's too many X's is kind of what I added onto it. I agree. It's something that's designed to help you if you want. But if you just want to use an ice table and X every single time, as long as you know what you're working with, that's fine. Okay, if we run through these, this is a little bit more specific. So we'll go ahead and say that this is different by having a before, shift, after. Initially, we have our 0.167. That's what we found for our molarity after we diluted it. And what we're doing is we're subtracting. You figure out which one would be your limiting factor. So in this case, the limiting factor when we have a 1-to-1 stoichiometry is our hydroxide. Hydroxide is the smaller number. So it's going to run out first, and we're going to have a little bit of hydrogen ions left behind. So we subtract this. We also subtract it here. She has this designation that it's a 1-to-1 ratio. And what you're left with is you have a hydrogen ion concentration of 0.0125 molar. And then to figure out your pH, you take the negative log of that. And that gives you a pH of 1.9. So in some ways, it's still fairly simple if you understand all the parts leading up to it. It is just adding another set of things to do to it. Okay, so if you wanted to look at these again, this is something very similar. Okay, so now we're looking at the pH when both substances are combined, and we have our perchlorate ion or hypochlorate ion, hypochlorite. Okay, so hypochlorous is going to be this one. It's not the same as what we had. This is HClO. This is a weak acid. All right, and then we have potassium hydroxide, which is still that strong base. So we have to take into account the creation of the perchlorite ion, and otherwise it's quite similar. A weak acid to the conjugate base. For a weak acid and strong base, pH is determined after an equilibrium. So now we have to run this through an ice table. Okay, so we found out what we had after that. We have this ion and this one. How is this different than the last one? Well, if the first one was a strong acid, and so it all shifted towards product, but we don't have all product on this one. Okay, we saw what was being offset, and we saw that this is involved still over here. Right, run your rice table. We were told the Ka, and then you can figure that out. pH is the negative log of what we found with this, our hydrogen ion concentration. You will note that this is a base. Does that make sense? Well, we had a strong base that fully dissociated, and we had a weak acid that did not. And so as a result, you're going to have a more basic pH. I can do some more where I run through these more slowly, if that helps. Okay, so this is another example. In interest of keeping this one short, you can look through these notes if you want. And again, I stress that you probably should watch these on College Board too. That would be helpful to you.